So last time, let me just like write this. We saw the Hodgkin, Huxley model. And this was to describe basically how action potentials are initiated and propagated down a neuron. Propagated in neurons, and we use this for nonlinear differential equations. So if you remember the situation that we were looking at, I had a cell membrane. This was the exterior. This was the interior. Then I had some sodium ions on the exterior, potassium ions in the interior. I was applying a current, right, from the external side in the inside. This was denoted as current applied. And then we were trying to measure with this model what is the output, the outward current, right? So that was the I subscript I. And let me just remind you, the model that we came up with, it was basically, we didn't come up with it, but we saw in the class, it was this. So this G was denoting the conductance, if you remember. And the subscript just denotes the ion. Then we had M cubed, H, V minus V, and A. And I will remind you what the different terms are. This was N to the 4, V minus VK. And then I had some leakage term, which was G, L. So this M, H, and N that I'm writing here are from these graphs that we were looking at last time. Basically, this is the sodium activation. This is the sodium inactivation, and this is the potassium activation. These were the conductance terms for the sodium and potassium ions. The V is the applied voltage, and these are the resting potentials for the different ions. And I was denoting by L, basically you can have different ions we said in these dissolved salts, but mainly we will have chloride ions. Do you remember this? Okay, great. So when I was writing down the differential equations for the different activation and inactivations of sodium and potassium, we also saw that we have a relaxation time, which was these tau terms. And we also had the equilibrium gate variables for the inactivation and activation variables, right? So I drew these two graphs last time, and I told you that you don't have their explicit form. So how you measure these things is basically experimentally. And someone was asking me, so I wanted to come back to this. This is not a time axis. If you look at the axis, we are looking at the applied voltage relative to the resting potential, right? So these quantities that you are seeing here are not a function of time. These are the equilibrium values already, and we are seeing how these depend on the applied voltage or current. Does that make sense? Okay. So if you want to interpret this, basically this is saying that at elevated potentials or voltages, you're seeing that the potassium activation, for example, is turned on, but the inactivation is being turned off. Okay, any questions so far? Okay. All right, so we also saw last time when we did those 6 steps, we drew the following diagram. So this is why we did the Hodgkin-Huxley model. Basically, it was to see how the applied voltage changes as a function of time. So we said you apply some external voltage to your system. So you start at time 0 with some applied V. And then this causes an action potential. So you input some energy in the system, basically, that gives you a small excursion before it returns back to its resting potential, right? And we said that this is how you basically get signals propagated from your neurons to your muscles, for instance, to do something. Okay, so today what we want to do is reduce this complicated 4-dimensional model into something that is more tractable and that we can analyze more easily, analytically. So the way we will do that is reduce the 4-variable system into a 2-variable system. And we will use something called the FitzHugh Nagumo model. And that will be today's lecture. So let me just write down this small summary that I said. So at this moment, this is a 4-dimensional system, and the 4 variables that you are solving for are basically V, we have N, M, and H. And these were described by equations 1 to 4. I didn't rewrite them yet today, but you have it in your notes. And I will say here, this is not easy to analyze. But we can reduce it to a 2-dimensional system called, it's again by 2 people, it's called FitzHugh Nagumo. So if you want to look at the type lecture notes, this will be for your reference, section 2.3. And this FitzHugh Nagumo model is basically an asymptotic reduction of the Hodgkin Huxley model. So in order to analyze this 2-dimensional model today, we will use a lot of phase plane analysis. Okay, so let's look at the assumptions in order to be able to build this approximate 2D model. So I'll list here 3 assumptions that will be largely based on those 2 graphs over there. So the first assumption that we can make is that the relaxation time for the sodium activation M, so tau M, is small. So you already see basically from graph 2 that in comparison to the other 2 is the smallest one. So this tells us basically that M approximates the equilibrium value. This, remember, is a function of the applied potential. And I have that tau M is much smaller than tau H and tau N. So how do I know this? Basically, you can look at, so here I will say that M reaches its equilibrium value, and I will show you why. Its equilibrium quasi-steady value rapidly. So if you just look at your notes, the equation number 3 was basically I had tau M, and then it was dm dt is equal to M, and then I had minus M. So now if I just like divide by this, and I know that is small, basically you will see that this is large, this is small, right? So M will approach M infinity quickly. Okay, so the next assumption that we can make to write the model is that now, if you look at the graphs again, it's a bad approximation, but anyway, this is how the model is done, and it can give us the underlying physics. is that this relaxation time for the potassium is more or less the same as the tau h. Okay, let's say it's more or less the same. So I have tau n, and I will comment that this is not perfect. Just see graph 2. But we will say for the purposes of what we are looking at, this is a decent approximation. Okay, and then the third piece of information that we will use from our experimental graphs is the following. So I'll now use this and say that if you add the blue, which is h infinity, with the green one, we will say that it's more or less constant, the sum of these two, okay? So that's the third one. We have that n infinity plus tau, sorry, plus h infinity is a constant. Let's denote this constant by h bar. And then I will say this is motivated by graph 1. And what I want to do is use this now to say what will happen if you sum up n and h, but that you can get from the differential equations that we wrote for these different activations. So just remember, using equations 2 and 4, you can basically write the following. I will sum up now the differential equation for n and h. This will now, because I also had from the differential equations, if you remember, n infinity and h infinity, right? It's of this form, basically. So if I sum their infinities, I'm going to get this constant. And then from the right-hand side, I will also have the n and h. So I'm going to write n plus h here. So if you want to solve this is a first-order differential equation for n and h, right? So we can solve it exactly. And we know that n plus h as a function of time can be written as h bar, which is this constant, plus some exponential with a constant c. Any questions so far?
Do we need to put the time scales in that equation?
Because we assume they are the same, no, right? Yeah. And yeah, no, you don't really need them. So now this system, I will say now, is true for all time. For all time. So if time goes to infinity, this thing is going to drop out. So we can say that n plus h is h bar. So it eventually settles down to this. All right, so in your second problem sheet, you will be able to basically show that with all these assumptions, what you can now do is reduce the Hodgkin Huxley model so the 4 ODs for V, M, N, and H to the 2D system that is now just a function of V and N. So I'll say here so that you know this is problem sheet 2. Okay, so the equations basically become the following. So I will have C subscript M. This is the capacitance. And then it's the derivative of the voltage as a function of time, the applied current from the exterior to the interior, minus, now I will have the conductance for the potassium ions, V minus Vk, and then for this one, we had the n to the 4, so I'm gonna write here n4, plus the conductance for the sodium, V minus the resting potential for the sodium ions, m cubed infinity V. So notice that here I wrote n to the 4 and here m infinity. This is the same as m by the first assumption, right? We have that it settles down to this, but you can omit it if you want. It's the same thing. And then I have plus, I guess this is the leakage one. And then I have the second equation. This is tau n. And then it's dn dt. And infinity v minus n. So this is the system now. And from having this now, this system of two ODEs that you can solve for, we will see that some of the parameters I will do a non-dimensionalization basically to be able to see this, are small and negligible. Okay, so let's look at the non-dimensionalization to be able to analyze the system. So we have that in general V will tend to the equilibrium or resting potential, V eq, right? So now I will do the non-dimensionalization for the voltage in the following way. So I will write V, this is small v, is the voltage minus the resting voltage divided by, and then I will normalize it by the difference between the resting potential for the sodium and the equilibrium V. So notice that if I want, for instance, this is nice because basically little v settles down to 0, right? Rather than V equilibrium. And then we will also non-dimensionalize the time. So the time will be given by tau n as a function of this t prime. So these are my two new variables. Okay, this is basically the voltage. Okay, so if you do the non-dimensionalization, plug it in into your time derivatives and so on, this will give you the following dimensionless system. So this reduces to, or not reduces, let's say this leads to the following dimensionless system. So it will be two ODs again, and I will write down 6 dimensionless variables that you get out of that, or parameters, not variables. Okay, so I will have an equation for the dn dt that will be just this. This is little v now. And then I will also have the equation for the v, which is the first equation over here. So I have dv dt, and this is, now I will get some parameter epsilon. I will define it in a second. This is some current, dimensionless current, minus Vn. So what is this G function, and what are the dimensionless parameters that we get out of the non-dimensionalization? So here this G, which depends on the voltage and the activation N, is the following. So I have G, Vn, and then of course you can already imagine it will depend on the conductances and these other variables, but in the dimensionless form. So gamma is like the G, but dimensionless. I have it for the potassium. This is V plus Vk star n to the 4 plus gamma L, which is the leakage one, minus VL minus 1 minus V, H minus N, and then I have M cubed V. Again, you can write M infinity or M is the same thing. So this is the G, and then we also have 6 dimensionless parameters. So my dimensionless parameters will be the following now. So first I write the current. So the current I star is just the applied external current divided by, and then I have the conductance of the sodium times the voltage of sodium, the resting potential of sodium basically. Then we also have Vk, this is this. This is going to be minus Vk over Vna. That's why I had a plus here rather than the minus original, because you have the V in the dimensionless parameter. This one we kept like this with the minus, so the VL will be VL divided by Vna. And then I also have the gammas that I have to define. Those are dependent on the conductance G. So maybe I will write it over here. Gamma K is G, K divided by G for the sodium. Gamma L, GL again by the sodium one. And then I'm missing the epsilon, right? I didn't define epsilon. Epsilon is the capacitance, which is the very left term in the first OD there, divided by GNA tau N. Okay? So you can actually show, if you do it formally, you will arrive at these equations, and these are your dimensionless parameters. Okay, so now how do we analyze this? This is the whole point. So now that we have reduced it to this 2D system for N and V, we will be able to say what happens for what is the fixed point, can we see if it's stable or unstable, and then draw some phase diagrams, okay? All right, so let's do that. So the key point in this FitzHugh Nagumo model is that the epsilon parameter over here is small. And again, you can like measure what the capacitance is and all these things. So you can get what the value is. So the key point here is, by the way, yeah, okay. Nothing, I was gonna point something to the graph, but it's fine. So the key point here is that the epsilon term is small. So remember, epsilon is this over here. So if we have that this is a small quantity, we will know that the V, which is this, basically this is really small now. So I will know that the V quickly reaches again a quasi-steady equilibrium. So let me number the equations so that we can refer to them. This is 1 and 2. And I will also tell you that the leakage gamma L is also small, and that you can measure. So if you have these kind of things, then you can just say, I'm gonna come to my G, which comes from the Hodgkin Huxley model, and I'm going to now use the fact that I know this is really small, and then be able to infer what the non-clients are for the phase plane analysis. So let's phase plane analysis. Let's do that. Okay, so I will start with the simplest case. I will say that I don't apply an external current, so my I star will be 0. So let's just start with that. So set for now I star is equal to 0. So if I set this to 0, I can see from equation 2, this will be gone, this is small, so I will have that G is 0, okay? So if we do that, if I look at equation 2, V is given, the V null client is given by G. You remember what null clients are? It's basically when you set that variable, the derivative to 0, right? So if I say dv dt is equal to 0, the current is 0, then it means that the null client is given by this. Okay, and remember that we also said that gamma L is small. So if I come here and I set this to 0, I can get an algebraic equation that tells me how the N is related to the V, the voltage. So that's what we will do next. So setting epsilon and gamma L to 0 in 2 gives the following algebraic equation. I have n to the 4 divided by h bar minus n, and then I have from this 1 minus v m cubed v divided by, and then I have these two terms over here, so it's gamma k v plus vk star. So this is an algebraic relationship for, and then we have v and n. And remember, the system we're trying to solve from equations 1 and 2 is for v and n. Okay, so if you take your favorite plotting software, you can actually draw this, or you can think about it yourself. You will basically get that G of v comma n, which is given by this, looks as follows. So this is the axis of n versus v. Remember, n is a function of v. And then I have that this is the null client. So this is given by G and v is equal to 0. Any questions? Okay, great. So now we can begin analyzing. So I have two separate regions. I have what is happening when G is negative, so below this null client, and what is happening above it, right? So how do we analyze this in phase plane analysis? You go back to your derivative. So let me do this. Now I'm looking at that scenario, right? So to get G, I was setting dv dt to 0. So I want to see if I'm above it, do I go to the right or to the left? Does that make sense? So let me get some different colors. So okay, so let me just look at equation 2 and now say dv dt is I star minus G divided by epsilon. And then see what happens if I have a positive G versus a negative one. So my equation is dv dt is equal to minus GVN divided by epsilon. We have already set the current to 0. So if I'm above, is G positive or negative? Positive, right? We are above it. So if we are above, this is positive. This is a small quantity. I have a negative though. Does V increase or decrease as a function of time? it will be negative, right? So it's a decreasing function with respect to time. So I know that it's going in this direction. This is g greater than 0. And I do the same below. Below, I know g is less than 0. Minus something negative is going to be positive, so I know this is increasing now. So the direction in which we are going is this. So v increases, and then here v decreases. Increases, right? This is the other way I wrote it. So this is increases, sorry about that, and this decreases. And so someone could ask me now, does the analysis here change when you have that the leakage conductance is not negligible? Well, no. Basically, the qualitative features of this would look the same. It's just the actual quantitative things would change. So if we didn't assume, it makes the whole thing easier if you just like drop that term. If we didn't assume gamma L is much less than 1, then the qualitative features wouldn't change. Okay, so this is the alkaline just for the equation that we had for V. I will now look what happens at the N alkaline. So to get the N alkaline instead, you have to look at what happens with equation 1, right? So the alkalines we said is when you set that variable to 0 when you differentiate with respect to time. So it just tells me that N is basically N infinity, right? That's much simpler. So I can also draw then what is on the same graph, what is the N alkaline now? So I'll repeat the one for G0. So this was the G, and it's the V alkaline. This was a function of V, and then this was N of V. And we said that from equation 1, we have that the N alkaline is N is equal to N infinity V. And that you already know from the experiment. So I drew there N infinity as a function of the potential, right? So we know how to draw that. It's just a line like this. It's an increasing function. And at this point over here, when I have that the V is equal to 0, I have basically a fixed point. Okay, so now we want to analyze what happens when you're between the two alkalines or above this alkaline and so on, so that if I give you any initial point in here, say I start here, I know where we will end up. So let me get again these different colors. And I will analyze in the same way with the signs what happens with dN dt. So remember from equation 1 again, I had dN dt is equal to N infinity V minus N. So if I'm in this region over here, so above the N alkaline, I know what is the sign of this? N is above the N infinity. So what do I know about dN dt? Great, exactly. So it's negative. It means that if I start somewhere here, it will take me towards the null line. Excellent. Okay, so I have this. Now I start at a point here. So here n is less than n infinity, right? So from that I know this term is greater than 0. So I know that n will be increasing, right? So it's taking me toward that. Is that clear for everyone? Okay, great. And from the previous analysis we did there with the dv in dt instead, we knew that this is increasing in this direction, right? I had this. And then in here above the v null line, we had that is a decreasing function. So what this tells us is that we can now take any point. So say I start here. This will basically tell me you have to increase the v for a fixed n. I go like that. And then I'm on the null line until a point I can no longer increase above. And then it basically drops to this value, and then you fall on your fixed point. And then you can do the same. You can start anywhere basically and see what the trajectory will be. So I will make a note here. So this is until we go back to the equilibrium. And then here maybe I will note, remember this axis is your voltage, right? And from the non-dimensionalization that is not showing now, I did the non-dimensionalization in the following way. So I had V minus V minus V and A minus V equilibrium. So if your voltage tends to the equilibrium value, we said that this basically goes to V equals to 0, right? In the dimensionless form. And this is exactly this point here, V is 0 at this point. Okay, and this is where both your V and your N dot are 0. So it's a fixed point. Okay, but it would be interesting to also do like a stability analysis of this. So we'll do a linearization. So you'll get some Jacobian. And then from that, we will be able to say if the fixed point is stable or unstable. If it's a node, spiral, we will be able to do this kind of analysis. Okay, so perturbing around the fixed point. We'll see that the trajectories, basically is what I drew already there, that the trajectories spiral around, so the fixed point is a spiral. But I will show this also with the linearization. So this is where stability now comes in. So we had the fixed point. The fixed point was when n was n infinity and the v was 0, right? This is this point here. So I want to do the linearization around that point. So linearize near the fixed point. And the fixed point was n infinity and v equals to 0. So the procedure is as follows. We said v is v plus 0 basically. And then I have n is equal to my fixed point plus some n where this n is small. So I will have v and n are both small quantities. Now if I consider back my differential equations 1 and 2 that I have on the other board, the ODE system becomes the following thing. So I will first write it down and then I will show you how we get that. So this is V. I will have a 2 by 2 matrix now. And then I will have N and V here. The 2 by 2 matrix is just -1 dn infinity dv minus 1 over epsilon from the equation 2. And then I have the derivative is partial because g is a function of both v and n. And then I have -1 over epsilon here, but with respect to v. And let's name this because I will be using it as the M matrix. So if you forgot how to do this, basically the way you do it is you obtain M by doing a Jacobian. So the Jacobian will just be the derivative of n with respect to n, and then I will have dn dv dv dn dv, and then I have this with respect to v, and I evaluate this at the fixed point. So the fixed point for us is, I said, n infinity and 0. You remember this? Okay, great. So once you have this, then you will also remember that when you were doing the stability, that I can basically determine now the stability of this based on the determinant of my matrix and the trace. So we have the stability is given by the determinant of the matrix M, which is this Jacobian, and the trace. Usually we write it like this, the trace. And then we have that, in the last 5 minutes, I will just tell you a bit about the stability. If the determinant of M is less than 0, you have a saddle. And if the determinant is greater than 0, and the trace of M is negative, then we have a node or a spiral. Okay, so the determinant is easy to write down. So first I will just write its value. So the determinant of M is just this. So I will just pull out the 1 over epsilon because it's in both terms. And then I have dg dv. The minus I can also pull out. No, it's not a minus because this is minus, minus, and then I have minus, it's also plus, so it's plus. And then I have dg dn, and then dn infinity dv. And we have that evaluated at the fixed point. Do you agree? Okay, and what is the trace instead? The trace is the sum of the diagonal entries, right? So I'm gonna write here -1 over epsilon dg dv, also evaluated at the fixed point. So what we want to do next is be able to say what the sign of this is, correct? But you can't do that. Basically, you can't, because we know what g is. G is a function of both v and n, right? So I can write down what its derivative is, and I can see what this relationship will be based on chain rule, basically. So what is g, if we still have time? Yes, we have 5 more minutes. So if I look at g, so g, remember, was a function of the applied voltage and n, right? But n is a function of v. So if I want to differentiate this, and if we look at the case where we're on the alkaline, what do I get? I want to differentiate this with respect to v. Isn't it this? Plus dg in the n and then n is just a function of n, right? So I'm gonna have this dv, right? But I'm looking at the case where I'm at the fixed point, so this means that I basically have 0, so I can rewrite this thing as dn dv is equal to, and then I just rearrange, so it's going to be minus dg dv divided by dg dn. Right, if I miss any signs or whatever, please shout out. But I think this is fine. So then we can basically say something about the slope of the null lines, right, based on this. So slope of the null line is basically going to be minus dg dv divided by dg dn, since the v null line is where g is 0. The slope of the n null line is equal to dn infinity dv, and the n null line, if you remember, was just n is equal to n infinity as a function of v. So since we have these two things, remember from the graph, so let me redraw it here. So from the graph, I had the v null line, which was this function over here. This was the v null line. And then I also drew the n, which was this. So this has a negative slope, right? Then it's increasing, then it's negative again. This has a positive slope throughout. And you can see that the slope of this in general from the graph is bigger, right, than the slope of the v null line. So from the graph, we have the slope of n null line is bigger than the slope of the v null line. And we know that this is basically bigger than this, minus dg dv dg dn. And if I know now this, you basically take it and you plug it into your determinant, which is this. If I rearrange this, this is just greater than 0. Epsilon is a positive quantity as well, so the determinant is positive. So this tells us that the determinant of m is greater than 0. So the next thing we have to do is look at the trace. So the trace of m was the sum of the diagonal entries of the linearization matrix. So basically it was, as we wrote down, minus 1 over epsilon dg dv evaluated at the fixed point. So now we just have to say whether this is positive or negative. So if the fixed point is stable, then we should have that the trace is less than 0, which tells us that basically this quantity over here, dg dv, evaluated at the fixed point, should be bigger than, so this is less than 0, it's going to be bigger than minus epsilon. So if we manage, now I don't have time to do it, but if we manage to show that the derivative of g with respect to v at the fixed point is greater than 0, it's definitely bigger than a small negative number, right? So once we get that next time, we'll be able to say what the stability of this is. Then I will tell you something about limit cycles. And once we finish with that, we will see wave propagation, basically in neurons. That's the next topic we are going to cover. That's tomorrow. Thanks.